Okay, so this video is continuing section 8.2 on the overview of photosynthesis, so really just the introduction. So we've already talked about the big picture of why photosynthesis is important, so we're going to look very briefly at the process, and we're going to talk a lot about the light energy. So really the process of photosynthesis gets broken down into two parts, 1 and 2. So that's what we'll see next. Okay, so the process of photosynthesis, like I said, it's got two parts. The first part is light-dependent reaction. So what it means is that it must have light in order for this part to happen. The second part is are called light-independent reactions. So they're independent, they do not require light in order to do this step. So this is typically the part of photosynthesis that happens at night. So when I look at the word photosynthesis, I automatically, my brain kind of breaks it into the photo part and the synthesis part. So photo, what that actually means is light, and synthesis means build. So if we look back up here at our two processes that happen, the light dependent and the light independent reactions, they coincide with this idea of photo, meaning light, and synthesis, meaning building. So we'll see how that works in a minute. All right, so we're going to focus on the photo part, understanding how light is involved in photosynthesis. So the first thing we have to understand is what the nature of light is. So light is described by waves, electromagnetic waves, and these waves are either absorbed or reflected by whatever surface they hit. Okay, so right here, we've got all of these different waves. How many of you have ever seen a prism before? You know, you like shine light through a prism and then you get the whole rainbow effect coming out. Okay, so what this shows us, what a prism shows us, is that light is actually made up of many different colors of wavelengths. So when we are looking at something, some light is being absorbed, as in taken in by the object we're looking at. Like in this case, the black billiard ball is taking in all of the colors. Okay, it's absorbing all of them. In the case of the red one is absorbing all of the colors except, curiously enough, the red one. So this red arrow is being reflected. Okay, so reflection is whatever it bounces off. It's not being absorbed. So we notice the white ball, it's reflecting all of the colors, which is why it appears white. So the thing that's a little interesting here is that what we're seeing is actually only the reflected light that's hitting that object. Okay, so we talk about light being made out of a wave, and each of these different waves, like you'll see, you know, they're different colors, like, oh, this guy's green, and this one's red, and this one's violet. But you'll also notice that the sizes of the waves are different. So each color has kind of a characteristic size. So here they're measuring the wavelength, so the top of one wave to the top of the next wave. And as we go from violet down, the wavelengths are getting larger. Okay, so because of the different sizes of the wavelengths, they also have different amounts of energy. So in terms of size, we've got larger as we go down towards red. But if we're talking about, so we'll make wavelengths be green. But if we're talking about energy, let's use a bright color like pink. All right, so the amount of energy, the shorter the wavelength, the greater the energy. So just think about if you are jumping rope. In order for you to jump rope faster, you have to spend less time on each individual jump. So like your jump time has to be less. So it's kind of the same way with the shorter wavelengths. The shorter the wavelength, it's going to have more energy. So shorter wavelength equals greater energy. That's the relationship that's important to keep in mind. So sunlight is made up of white light. Now, if we remember from our billiard ball, white light is all the colors. Okay, so we come back down here. If you've ever seen like a spinning wheel that's got all of the colors of the rainbow on it, but when it's spun, it makes it look white. That's a way to kind of see it. A prism, so just kind of like a triangular prism, you apply a beam of light to it and then it separates out into its different components. Those are all ways that we know that sunlight is made of all the colors of the rainbow. So we have to understand sunlight, because sunlight is what we're using in photosynthesis. So now we get back into the plant. So the plant has got special molecules called pigments that are basically just capturing the energy in light. Okay, so they're absorbing energy. And so the interesting thing, like we're used to seeing a lot of green plants. So green plants have got a specific pigment that makes them look green. Keep in mind, if we're talking about what we're seeing, it means that green is what's being reflected. So it means that the red is being absorbed. It means that the blue is being absorbed. All of the other colors of the rainbow that are not green are being absorbed. Green, however, is reflected. So what that means is that all of these other colors of the rainbow, okay, except for green, are being absorbed by that plant. That means the energy from them is being absorbed by that pigment. Now there are other colors of pigments, like what we're seeing in the fall. And so, you know, basically the same thing as we just talked about with the green chlorophyll, only instead of it being green reflected, it could be yellow or red or whatever color it is. So chlorophyll, like I said, this one is the most common. This is what we see in the chloroplast, which is the organelle that does photosynthesis. So chlorophyll does a really good job of absorbing violet blue rays, which, keep in mind, are going to be your highest energy. And it also does a good job of absorbing red light. Okay, so it reflects the green light, that's why it looks green. Other pigments, you know, like reds, yellows, carotenoids, they're going to absorb violet through green very well, but not so much the lower energy ones, which kind of makes sense if you're thinking about, you know, in the fall. In the fall, you have less sunlight, so you need more of this high energy light in order to help the plant survive. Okay, so why are pigments so important? We know that their job is to absorb energy or sun energy. So how do they do that? The way that they're able to absorb the light energy, the waves, the energy in these waves, is by exciting electrons. So what that means is, so let's just imagine that a bit of light is hitting an individual pigment molecule. So that pigment molecule, what happens is it's hitting an electron and it excites that electron. So notice right here, the electron is close to the nucleus. It's right here. All right, so the nucleus is the plus, it's close to the nucleus. When it gets excited, it's actually able to jump to another energy level. So it's actually an excited electron. Okay, so the whole job of the pigment is to absorb the sun energy so that we get these to get excited electrons. All right, so that's it for the photo part. So photo, we're taking light energy, we're absorbing that energy by using pigments. Photosynthesis, now we focus on the back half, is where we're building. So we're taking in this light energy, and now we're going to be building. The real, we know that we've got two byproducts of photosynthesis. We've got glucose and oxygen. But what we're really kind of focusing on here, what's really the important thing to the plant, is the glucose. So we're going to build this large molecule of glucose using the energy from these excited electrons. So where energy comes from. Okay, so the excited electrons from the light are going to provide the energy we need in order to build this large molecule glucose and make the sugar. Okay, so the interesting thing, if you've ever heard of like free radicals before, basically what a free radical is just like an electron that's got a lot of energy to it. And so those electrons can actually be kind of dangerous to a living thing. We know that free radicals can cause cancer. So what happens, instead of just this little excited electron, pretend that's an excited electron, just being able to roam free, it is held by another molecule. So there's like a carrier that's grabbing onto this electron so that it's not going to cause damage with other substances in the cell. So they need a carrier so it doesn't damage other cell parts. All right, so the electron carriers that we use in photosynthesis, or that plants use, is something called NADP+. And when it has this extra electron, it becomes NADPH. Okay, so remember, an electron has a positive charge. So, an electron has a negative charge. So when we add that electron on, we make it a neutral molecule. This slide is an analogy about kind of what an electron carrier does. So think of the electron as being this hot potato. So see here, it's actually two electrons. So we see the E and the negative. Those are both signs that it's electrons. We have two of them. There's also this little hydrogen with a positive charge. So what ends up happening, in order for this NADP+ carrier to grab onto the electron, it's also going to grab onto a hydrogen as well. So notice how this mitten is going to allow us to grab the hot potato, but it's not going to hurt our skin. So what ends up happening is when it grabs the two electrons, it also ends up grabbing this hydrogen. So keep in mind, we've got a charge of -2, and then we have a charge of +1. We overall have a charge of -2. But keep in mind the NADP+ overall had a charge of +1. So, oh my gosh, I can't even do math right. Okay, so -2 + 1 gives us an overall charge of -1. Now, NADP+ has a charge of +1. So overall, once all three of these things are together, we end up with NADPH, which is neutral. So it's just holding on to these electrons so that they can't damage anything else in the cell.